Hi everyone, thank you for watching this video. My name is Yang-Zhi Chou. I'm going to talk about localized surfaces of a topological insulator. Topological insulators are characterized by the insulating box and the robust metallic surface states that avoid Anderson localizations. Topological insulators with interaction is well studied, and we know there are three possible outcomes on the surfaces. The surface can either develop gapless metallic states, or it can develop a gap symmetry broken states, or it can develop a gap topological order. Here I list the possibility of the surfaces for the TI with only disorder or TI with only interactions. And I would like to ask, are these possibilities exhaustive in the presence of both disorder and the interaction? This is a very important question because experiments often rely on the surface state properties. In this talk, I will show you that new kind of states can arise on the surface of a topological insulator in the presence of both disorder and interaction through a mechanism I call the inhomogeneous symmetry breaking. The surfaces can become gapless and insulating, reminiscent of the Anderson localization. However, the surface still contains some characteristics that can be viewed as a remnant of the bulk topology, which can help the future experiments to identify new topological quantum material even when both disorder and interaction cannot be negligible. In this talk, I will focus on two stories. The first story is the helical edge state of a two-dimensional topological insulator with a disorder and interaction. And then the second part, I will generalize the idea to three-dimensional topological insulator of class C2. So now let's discuss the first part. As I mentioned, I want to focus on the helical edge state as a rise from the two-dimensional topological insulator with a time reversal symmetry. The low energy dV of the topological insulator edge state is a one-dimensional massless derived equation. Importantly, the chemical potential of the system is not pinned to zero. There is a freedom to vary the chemical potential as long as it's inside the bulk gap. Time reversal operation is anomalous such that the normal backscattering is not allowed by the time reversal symmetry. Therefore, in the absence of a time reversal symmetry breaking, edge state remain to be ballistic. We can also use the time reversal operation to enumerate all the possible perturbation terms. The leading disorder term is nothing but the chemical potential fluctuation. And we model it by a white noise Gaussian correlated zero mean disorder. The leading time reversal symmetry backscattering interaction term is in the form as L dagger R square. Because this term now is a time reversal even. Importantly, there is a factor that keeps track of the incommensuration of the lattice wave vector. So this backscattering interaction is actually a Unklapp term. Only when 4K Fermi is commensurate to the lattice wave vector, it might have some effect. Otherwise, it's generically irrelevant. And we also consider Luttinger liquid interaction. The helical edge state with only time reversal symmetry disorder is topological protected because the backscattering is absent. The helical edge with only unclap interaction is related to commensurate-incommensurate problem. And the conclusion is that unless commensuration is satisfied, otherwise the 1D edge state should be ballistic. The commensurate-incommensurate problem can also be understood by this simple picture. We first assume that Dirac point opens up a gap because the unclap term, and then we remind ourselves that the 4K Fermi or the K Fermi is determined by the chemical potential, and the commensuration condition is nothing but the chemical potential inside the interacting gap. Generically, the chemical potential can be tuned outside. They remain to be ballistic event can be enhanced because the disorder will relax the momentum conservation. One simple way to understand this process at a low temperature is through the figure here. We consider that the disorder is slowly varying, and for the dispersion at the Dirac point, the unclap term open up an interacting gap. Previously, the chemical potential is not at the interacting gap, and that is that's actually true on average, because the average chemical potential is not within the gap. However, when we consider disorder fluctuation, there will be some region that shows a local commensuration, even though the commensuration is not satisfied on average or globally. And when this region satisfy the commensuration, backscattering will happen. It's quite intuitive to argue for the existence of insulating localized edge. But if we want to understand the localization property, we have to do some more rigorous analysis. For example, we can perform bosonization of this disorder interacting dV. In this notation, the theta is a phonon-like field, and the k smaller than 1 is repulsive interaction, which will be focused in this talk. K equals to 1 is a non-interacting point. And with the bosonized form, we can derive Rg, which suggests that there is a localization instability for K smaller than 3A. However, this result only tells us about the existence of instability. It does not tell us what's the physical interpretation. Moreover, we would like to know what is a localized object. So that's why we still need the other two analyses in the strong couple phase. First, we look at the semi-classical limit, where the Hamiltonian can be approximated by these two terms. And with a given fixed realization of a disorder potential, we can perform a domain wall analysis. And we easily conclude that as long as V is a Gaussian disorder unbounded, it's naturally to realize kink and anti-kink configuration in the theta space. To make a long story short, let me just conclude the property of the ground state. First of all, ground state will break a time reversal symmetry spontaneously. However, it's in a spin glass-like fashion. And here I performed an analysis for a commensuration condition, but this can be generalize to more generic situation. Another place we can make progress is at the Luther-Emery point, which corresponding to k equals 1/4. We can perform refermianization procedure for this theory, and the originally interacting propellant will be mapped to a non-interacting propellant. The Unklav backscattering term will be mapped to a mass term here. And this theory was studied by Boutrout in 1999. He showed that every eigenstate is Anderson localized. And we can further use the property of the density and the current operator between the Luther-Emery theory and the physical theory, because they are simply related by a factor of 1/2, to infer the physical property of the state. Because the Luther-Emery theory shows the Anderson localization, that suggests the DC conductivity equals to 0, compressibility is non-zero, and the same applies for the physical state. So without actually solving the ground state in the physical basis, the physical fermion basis, we conclude that the ground state is a compressible gapless insulating state, and purely based on the Luther-Emery analysis. Luther-Emery fermion actually carry half of a charge. So, and this half charge notion is consistent with the semi-classical analysis of the kink and the anti-kink. Therefore, we can conclude that the localization is as if there is a half charge particle being localized. Another striking feature of the theory is the non-monotonic behavior in the localization. Namely, the localization is the strongest for the disorder in some intermediate value. This intermediate value actually corresponding to the disorder fluctuation is comparable to the incommensuration. In other words, the average chemical potential to the gap. Let me summarize the first part of my talk. Here is the phase diagram of the TI edge state in the presence of both disorder interaction. I want to emphasize a few of the experimental signatures. The DC transpose signatures would be similar to the Anderson localization insulator, which is not a good news. However, I argue that since the localized object is half charge and the localization then shows non-monotonic behavior, sharp noise measurement possibly can reveal the half charge fluctuation. The NV center type of experiment basically measure the finite Q conductivity, could possibly provide some way to identify the non-monoticity in the localization. And perhaps the momentum resolved tunneling spectroscopy can also help us to identify this interesting state. Now let me go to the second part of my talk. First, I show you a periodic table for the topological phases. I already demonstrated the possibility of a localized 2D phase of a class A2, and now we want to find the possibility in the 3-dimensional system. And because the propellant is harder than the edge state, we have to come up with a general strategy. First of all, I will try to classify the possible instability of the surface theory, and then in homogeneous pattern with zero mean mass, and then First of all, I would like to show you an example that cannot be localized. That is the class A2. Class A2 is characterized by the time reversal symmetry, and the surface state is a single Dirac fermion. The only mass term is in this sigma z form, and we consider mass square interaction. When U is sufficiently strong, the system will develop a gap and break the symmetry spontaneously. This mass term is a topological mass. When it's uniform, it actually drives the system to a half-integer quantum Hall effect. Our goal is to find a gapless insulating surface. Therefore, we build up on the previous understanding and assuming a mass is a random function in space. And in this case, with a single mass term, there exists a massless domain wall. And because we assume integrate over the position, m of x is 0. Therefore, the domain wall is percolating. So it realized a percolating chiral network model. This model is robust against an function. They conclude that the 3D the example I would like to today is the class C2. It's characterized by time reversal symmetry and particle Hall symmetry, therefore chiral symmetry. And the topological invariant is Z2 invariant. The topological non-trivial theory contains 2 Dirac fermions. Therefore, there are 4 possible mass terms, among which there is a mass term that breaks the particle symmetry but preserves the time reversal symmetry. And this brings down the C2 state, C2 surface state to an A2 system because the particle symmetry is broken. And with the assumption of homogeneous develop domains of a topological insulator and the domains of trivial insulators. And we assume that average over the space, the mass is 0. Therefore, it guarantees a helical domain wall network model. Previously, I showed you that for k smaller than 3/8, the edge state demonstrate half charge localization. Then it also applies to the case here. So therefore, we know that this is the right scenario we are looking for. However, in this system, it also contains a junction when the edge states are close to each other. So we want to analyze the interaction and the perturbation from the junction, and this also realizes an interesting platform for the interacting network model, which was not studied before. We can enumerate the possible perturbation by symmetry at the junction, and we focus on these 2 processes. Those 2 are the inter-edge backscattering terms. And the inter-edge backscattering term, when both of them are relevant, they will form a local gap at the junction. This happened for a k smaller than 1/2. And let's remind ourselves that localization instability happens at a k smaller than 3/8. And what this means is that the local gap at the junction actually happens before localization instability happens the part. So this allows for realizing something clock state, which I will discuss in the next slide. Now, let me show you a phase diagram of the surfaces of class C2 under the particle Hall symmetry breaking. In the presence of interaction, there are three possibilities. For weak interaction, the helical network model remains to be delocalized. For quite strong interaction, the 1D segment become localized because the mechanism I mentioned in the first part. And there is an intermediate regime. The junction is locally gapped. The breaker spontaneously only at a junction. However, the 1D are localized. So here is a summary of the second part. I want to emphasize that the interacting helical network model and the possibility of realizing the clock state can be applied to weaker topological insulator and possibly the twisted biagraphene with a tiny angle. In the beginning of my talk, I show you that topological insulator with interaction have three possibilities. Now I hope I convince you that there is another possibility, that is a gaply localized state with a tensor symmetry in a random way, with a symmetry breaking in a random way. And it might be interesting to explore the possibility of surface topological order with a disorder. I will stop here and thank you for watching this video.